So another way in which human interaction can, harm, I guess, or take us out of this dynamic equilibrium is going to be through dam construction. So if you think as the base level, meaning the place where the water wants to get to in the end, as being the sea or even an internal lake, those are going to be the base level streams. So if point A was going to be the source of the tributary system or the drainage basin, and then point B was going to be the base level, when we add a dam and hence a reservoir behind that dam, the new base level is going to be that dam. So if you think of A as being up here and the initial B being up here, now we're adding another point, a point C right here. And so now any sediment or water, I guess water with the sediment, that is trying to travel to its base level, it only wants to travel over here. So all the sediment that was initially going to point B is now being deposited at point C. So whenever you are building dams, it is very, very common to see a lot of sediment deposition near the reservoir on the sides of them. And you are going to see a depletion in that sediment load at the base level or at the initial base level prior to the dam construction. So that is another way in which we take the system out of equilibrium. So we've already talked about this particular graph a little bit, but I wanted to make sure that you saw an effect from it that I perhaps did not touch base on. So I talked about the lag time between the amount of rainfall that fell and the discharge that happened in an urbanized area rather than an area that was not urbanized, or before it was urbanized, I should say. So we know that an area that has been built, you know that the lag time between the rainfall and the maximum discharge is a lot smaller. But also because that lag time is smaller on the left-hand side, so on the left-hand side of this curve is smaller, it's also going to be smaller on the right-hand side, meaning the events are going to, or the amount of water overall that is being discharged has got to do so in a smaller period of time. So if you think about it in this way, both of these curves, this curve on the left-hand image and this curve on the right-hand image, both have the same area under the curve. So because they have the same area, they need to have the same amount of units, if you would. But on the left-hand side curve, this is a lot more spread through time. So in order for the right-hand side curve to have the same area, it needs to have a smaller amount of time it needs to be a smaller amount of time and a higher magnitude event for it to have the same area under the curve. So what that means is that every time that we have rainfall, we're going to have the effects from it a lot faster and also a lot stronger. So perhaps what used to be over here on the left-hand side, what used to be a 10-year flood event, now for us is going to be a 50-year flood event because of the magnitude that now that maximum discharge is going to have on the urbanized section of land. Another effect of urbanization is that we're going to have less groundwater. So if you think about it, because we are speeding up the rate at which water goes from the source to the stream, so that lag time is decreasing, less water is going to actually infiltrate into the ground, right? And as less infiltrates into the ground, less of it becomes groundwater. So groundwater has a purpose that perhaps you've heard of, that is very cool. So in times when the stream is low, many times the groundwater, if it is at a level that is high enough, it can actually feed into the stream. So it is actually very beneficial for dry times during the year where surface water is not enough, and so groundwater will contribute some of its water into the stream itself. So in this case, where we don't have infiltration and hence forming of the groundwater, we are not going to be able to input some of that groundwater into the surface water during that dry season anymore. So that is one of the bad things about urbanization. If we speed up the time, there's no longer infiltration into the groundwater, which in that case will no longer be groundwater that can be poured out into the surface water during dry times of the year. Another thing that can happen is that there can be water and sediment pollution. So many times, due to the groundwater actually serves as a kind of cleaning way to clean the water. Not the groundwater, but the ground itself will be a cleaning service to the water. So the water will travel through and infiltrate into the ground, and as it does so, it will basically clean itself out and then flow into the stream as clean water. So without it going into the groundwater, cleaning itself, and going back into the stream, the water will remain dirty, if you would, or polluted. So that is another disservice of the lesser groundwater from the speeding up of that lag time. Another cause of human interaction is going to be, and urbanization, I should say, is going to be that bridges may actually cause the flash floods themselves. The bridges are going to act as kind of barriers in which sediment and other things that the water carries along with it, such as logs or garbage, are going to get stuck, and they're going to create some sort of dam. So once enough water has built up behind that dam, it's going to create a subsequent flash flood after that smaller dam. So bridges, in this case, are the harmful kind of phenomenon, as you're seeing here on the left-hand picture. Some ways in which we can minimize the hazard of flooding. Some of the earlier and yet still used ways are going to be these physical barriers, such as levees, flood walls, or reservoirs. So a levee, as you're seeing here, is basically going to be building up the ground higher on the floodplain itself, so that when the river, when the stage, I should say, gets higher and higher, it will no longer flood the floodplain that it was originally going to, but it will still be contained within the barriers that were created. So these over here are going to be the levees, as you're seeing. Back to the left, all of that is part of the floodplain of this river. So what they hope to do is that by raising up this levee right here, if the stage were to be anywhere below the levee, then the water would not actually flood into its original floodplain. So this is actually a very good idea and used in many instances. In this case, they were unlucky enough that the levee sediments were so saturated that they actually gave. So this is caused saturation-induced failure is what it's called, because the sediments were so saturated, a landslide literally happened. And so the sediments gave in, and this whole side of the levee kind of collapsed into the river. However, hopefully some engineers took care of that and were able to repair this collapse in order for the levee to still be in place and used. So kind of on the other side of the spectrum, where we're no longer kind of adding parts, but we are letting the river do its thing, is channel restoration. So you're seeing here on the image what it used to be before. This river right here is pretty much engineered, if you would. So you can sort of see the line, the pretty straight line that was dug initially for the river to travel through. And then you're seeing that this river is kind of taking over with the flooding events. So the river restoration, channel restoration, is pretty much allowing the river to go through its flooding courses and then take its natural path. And we may help it along by perhaps planting some more vegetation on the sides of them that will create, more resistant banks, and not constructing any infrastructure near the banks of that river, near the floodplain. So here is what happened after. You still see kind of where the main channel that was initially constructed used to go, but you're seeing that now most of the water is going through a different path. So that channel is now going back to what it should have been, and you're seeing also a lot more vegetation than you did on the image before, which is cool. So this is actually a thing that is done very frequently now with more and more events occurring. Here in the Boise River, for example, you see that it goes through town, and there are certain areas where the river looks like this. So it looks a little bit straight, and you see that there's a lot of buildings, for example, nearby them. But there are other areas, for example, in the reserve, that the river is kind of let do its thing. So we have planted vegetation. We haven't done any infrastructure construction in those areas, and we're letting the natural stream take its course. So in fact, the Boise River, to many of us, it looks kind of like a straight stream or perhaps even meandering stream. The Boise River in nature should be a braided stream. So if you look at pictures way back, say in the 1950s, 1960s, when none of the dams or only one of the dams was built, you can see the braided structure of the Boise River, which is pretty cool. So that is one or another way to minimize the hazard from the flooding, is to let the rivers restore to their natural course. Another way in which we can minimize the hazard from, in this case, a meandering stream and the potential from the stream to erode on the cut banks is through the use of what we call riprap or gabions. So you're seeing both of those on the right hand side, both pictures of those. So the riprap is going to be just big boulders that are placed on the cut banks of the meandering stream. So you see right here, these would be where the riprap would be placed on the cut bank of the meandering stream, so that the meandering stream wouldn't erode further on that side and continue to do so further away. Same thing with the gabions, they work the same way. Gabions are not going to be big boulders like the riprap are, but they're going to be smaller, kind of cobble-sized material that is encaged in this metal little cages. So they're kind of like a square cage full of rocks. And make sure that you know that, because both of those are going to be on your quiz. So gabions and ripraps. So they work the same way, and this is very beneficial when you have infrastructure on the cut bank sides of the stream. So if I were to place my house over here, the natural course of the stream would be to continue to erode this cut bank and eventually get to my property. But with the placement of riprap or gabions, then it's going to be a lot harder for the stream to cut through that side. So because obviously the riprap and the gabions are going to be much heavier and much harder to move. So in this way, we sort of let the river take its natural course. So let it meander without it meandering so much that it's, influencing or damaging our property. The way to minimize the hazard is going to be channel restoration that can occur naturally. So in very arid areas like LA, for example, whenever you have high precipitation and perhaps kind of like flash floods, you need some sort of containment area. So in the past, they would have this big kind of channels through which the water would flow through. So here you're seeing just a little stream, but at times the amount of water was so high through the areas that it would occupy the whole channel that was constructed. However, this would cause a lot more sediment to travel through there, and perhaps even damage to the infrastructure that was in place already. So what they have done is let the channel kind of do its thing naturally, place some vegetation, which will slow down dramatically the speed of that river. So still make some sort of confinement where the flash flood, if you would, water would go, but now fill it up with vegetation that will slow down the speed of the water, and it will also catch a bunch of the sediment that water was carrying along with it, and prevent the harmful damages to the community and to the infrastructure nearby it.